So this is a video, and this is a continuation of the previous video on that this continues from the results that we left on, and the results we are achieved by our heuristic arguments, obviously. So this is the same thing that we really ended up on, and just phrased in a different way. Obviously, we let V form a vector space over some field F. Now, S, the spanning set, obviously is a subset of V, but since we are not giving a structure here right now, we just say it should be a finite. It should be a finite subset of F, obviously, such that it spans the space that we are working with, and then we just sort of introduce another set, the linearly independent set. Yet we won't say it because we want our theorem, our lemma to sound a different way. It should also be a finite subset. Now, the theorem starts by, because the consequence only resides but on the fact that if S is linearly independent set or not. So it states that if L is a linearly independent, L is less, then the cardinality of the spanning set is greater than equal to cardinality of the linearly independent set, the less. And not only that, but it also says that obviously this result is true, but also that we can find a subset in S, which we just defined as, which we just worked out, and we know how its cardinality would be defined and what it can do indeed. Moving on from this. So now comes the point of the proof. Let's I mean, in the beginning, talk something about the structure. Obviously, we can say for the sake of formality, now let us give a structure to our sets. Also, and obviously, as we defined it before, but for the sake of formality, such that L is less linearly independent set. Okay, done with the formality. Now, obviously, in this case, so the idea is to fix N, defined as the cardinality of the spanning set, and induct on M, defined as the cardinality of the linearly independent set. Now, well, obviously the base case would be M is equal to 0, but for a much thorough analysis, let us consider also the case of N is equal to 0, so that all the degenerate cases are taken care of. So, should I say started? Let us let's introduce it as a question. Not if N is equal to 0. This implies obviously that spanning set is the empty set. So which okay, but since we know something about our vector space, that is by the fact that span of S spanning set should be our vector space, which obviously implies span of phi is the trivial subspace. So this implies this is true. So this is the space that we are working with. Since L is a subset of V, but not any subset, it's a linearly independent set. So first of all, we only have two options for it. Either it's phi, the empty set, or it's the set itself. Since it's a linearly independent set, it cannot be the trivial subset. It has to be the phi, which implies L is phi. Since we know something about the S prime, we know something about S's and L's, which, how should I say? 0, which implies that S is also phi. Sorry, S prime is also phi. And if S prime is also phi, then obviously span of L union S prime is equal to span of phi union phi, which is just phi, and span of phi is just the trivial subspace, which is so in that context it holds. The second context, technically the first point would be, is this is the spanning set greater, and the cardinality of spanning set greater than or equal to the cardinality of the linearly independent set. Well, in this case it is true, because cardinality of spanning set is equal to the cardinality of floor, as 0 is equal to 0. So we are done here for at least. Let's move on to the main proof. Okay, since it holds for n is equal to 0, we know that, so we just have to work for n greater than or equal to 1, so greater than 1 cases. So now we can just say a different statement. We can just say fix n, any number that is greater than or equal to 1, and induct on m, obviously, since we took care of the degenerate case. Okay, so base case, obviously. So for m equal to 0, this obviously implies that L is equal to 0, which implies L is phi, obviously. So if L is phi, then the cardinality of L is 0, obviously. Does the first statement hold, that is the cardinality of the spanning set is greater than or equal to the cardinality of the linearly independent set? Well, that's obviously true here. Why? Because how should I write it? Because 0 will, which is equal to the cardinality of S, is greater, less than or equal to 1, which is obviously less than or equal to n. So this obviously holds. It's TFS. So this holds, obviously. Now the second part is, so does there exist as an S prime? Well, since the linearly independent set is phi, we can just pick S prime to be the original spanning set. Why? Because then we can get the statement can still hold. What I mean by that is, pick S prime is equal to S. Why? Because then the span of L union S prime would be equal to the span of L union S. But what is L? L is phi. So span of the union, okay, union S, okay, which is equal to span of S, which by definition is the vector space we are working with. So we are good. So our lemma holds for the base case. This is the first part of the proof. Now obviously we will have to write our hypothesis. So essentially we will say the lemma holds uh, for all linearly independent sets of size m-1, because we then would prove it for the case Lm. Rather than saying that, let me explicitly write the hypothesis. So essentially this is how our hypothesis will be. That is, if this set, obviously it doesn't have n m elements, it has m-1 elements, because we would want to prove it for m elements, is linearly independent subset of V, and S is the spanning set, obviously, then the size of the spanning set is greater than or equal to the size of the linearly independent set. And that exists as a S tilde. Why not S prime? Because S prime would be later for the case of M elements, obviously, with cardinality like this, and it spans the space of union with the linearly independent set. So this is our hypothesis, and our inductive step would be that simply H holds for all such li's. So n is equal to 1, 2, 3 up to m-1. Okay. Now, given that this is true, now consider same as we did before. We can consider itself as we did in our heuristics part, which belongs to L, which obviously is a subset of V. For the sake of formality, right now we are doing this. We can now say by H, we know something, that the span of L sub m-1 union with S tilde is equal to V sub F. Now we would like to exploit this fact and write L sub m in terms of the elements of these two sets, but for that we need to know something about the structure of L tilde, S tilde, since is equal to minus B. And the size of S is obviously n. What is the size of L sub m-1? Well, it's obviously m-1. So we can say that the size of S sub tilde is n minus m-1, which is equal to n minus m plus 1. If this is the size of S tilde, then we can define S tilde or have a structure to it. Let S tilde be equal to S sub 1 comma dot 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 S sub n minus n plus 1. So this is the structure of S tilde that we will take. Now obviously we should be able to write L sub m in terms of the union, because it's in the span. Let us do that on the next page. So I have written explicitly what the union is now, because this is the L sub m-1 and this is the S tilde. So since this should equal to this by hypothesis by H, I should write that by H, and it contains obviously L sub m. This implies that we should be able to decompose it in a following way. On to m-1, let's go with A and A for L's. Like this. n minus m plus 1. This will be b's. Okay, now note that this equality holds because of h. First of all, since this equality holds, there is a consequence that comes out of it. Technically, there are two consequences of it, and these two consequences help us to prove results that we want. First consequence is that there must exist at least one sub j not equal to the 0 vector y for j's in for j's in, I should say 1 to n minus m plus 1. Why? Because, see, if not, then L sub m is equal to j is equal to 1 to m minus 1 sub j sub j, which is a contradiction because L sub m belongs to a linearly independent set. But this is a contradiction because L sub m belongs to less. So we cannot write it in terms of the vectors in the linearly independent set. So if what I'm trying to say is, therefore, this implies that the cardinality of the S tilde is at least 1. So what I mean by that is cardinality of S tilde is at least 1. But we know what cardinality of S tilde is. It's m minus m plus 1. So this implies that minus m plus 1 is greater than or equal to 1, which implies that n is greater than or equal to 1. It's equivalently saying that. And this is one of the results that we would want to prove. So this is sort of part 1 of the lemma is done here. We will analyze later on why it cannot be in the opposite way like we did for the heuristics, but this is a strong argument here. And the second argument is that there exists at least one b sub j not equal to the 0 of the field. Why? Because if not, then again the same thing happens. Which is a contradiction. Because L sub m belongs to ls. Okay, done with that. Since there exists at least one b sub j not equal to the 0 of the field, here again without a loss of generality, let b sub 1 be the non-zero. Okay, if b sub 1 is the non-zero one, we can obviously extract b sub 1 from here and divide by it and solve for s sub 1. This is pretty easy and can be done in one swing. So here it is, obviously. The index of this one changed because that is the index of this one changed because that is what we extracted out of it. So index must go from 2 now. And obviously this can be entailed with this one, and this would obviously be like a sub m would be -1 here. So this can be rewritten if you would like as we sub what we want m we sub j sub j 2 n minus m plus 1 sub j. Now since this is just the span of L sub m, that is the original, this is the L sub m, the original n, and this is just the S tilde, we can simply say that it's 1 sub m. This start from S sub 2, so not exactly the S tilde, sorry for that. But this is obviously here true. Now this set is obviously our original n, original L. So what must this be? Well, we can just define it to be S prime for now, and this is a sharp I, but given the structure of this set, we will conclude that it is S prime. But anyway, let us just see. First, let us do a comparison. Okay, since span of L sub m minus 1 S sub 1 dot L sub n minus m plus 1 this is YH, and S sub 1, it belongs to the span of L sub 1 comma dot 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 sub n comma. Again, using the fact number 2 of our first video, the only difference between this and this is that we are missing S sub 1. Since it contains S sub 1, we are no longer missing it, and if this spans our original vector space, then so does this. Oh, well, now we can just name it a different thing. Union S prime. Which obviously implies that S prime is equal to but just naming it S prime doesn't do it any justice, because the justification for S prime would be its cardinality. Let us find its cardinality. Which is obviously what? Well, it's n minus m plus 1, but you skip a 1, so you just subtract it by this. Which obviously is So it holds. And this is the technically the proof is complete here, but it's not a good place to stop, obviously, because we still have a justification to present. So we will end with the final remark, obviously. See, n being greater than or equal to n was an obvious consequence of L being the linearly independent set. Well, what if this is not true? So what we say is, what if n is less than or equal to m? I'm just less than m because for the equal to case we already know it holds. So what if n is less than m? Well, if n is less than m, this implies that n minus m plus 1 is less than 1. But what is this? Well, this is the cardinality of S tilde. Less than 1. Okay. Cardinality of S tilde being less than 1. What does that even mean? Well, there are cases. Well, first is that S tilde is the cardinality of S tilde is 0. Second is that the cardinality of S tilde is negative. There's also a third possibility that it's a fraction. These two don't make any sense because this is a set and its cardinality being negative or fraction doesn't make any sense. So the case that we have to deal with is bigger. So suppose this implies that S tilde is P, which obviously implies that L tilde m minus 1 union S tilde is L tilde m minus 1. But since span of L tilde minus 1 union S tilde is equal to, this is by H by the way, V of F, which implies that this is a problem because now consider any L sub j which is obviously in L sub m minus 1 or which is in V sub f, obviously. Consider any this in I should technically write L sub m minus 1 is a subset of V. Then by this statement we should be able to represent it as a linear combination of elements in this set. This implies that L sub, let's call it J for now, as we did. I just have to write a different index for here. 1 to m minus 1 a sub I, and which obviously is a contradiction because L belongs to a linearly independent set, because this which implies the negation of the original statement is true, which implies that n must be greater than or equal to n. So this is a good place to stop, obviously. End of the proof and a formal argument for the Steinitz Exchange Lemma.